Same exact ideas, but we're going to move on to propane. Okay, so ethane only had 2 carbons. So now we're going to talk about propane, which has 3 carbons, right? And its different various conformations, okay? So if I draw propane using the bond line structure, I would draw something that looks like this, okay? And to start this conversation, we're going to take our bond line structure and we're going to draw the Newman projection for it, okay? So if I want to draw the Newman projection for this guy, let's imagine that I'm looking down this bond axis. So if I were doing that, what would I say? I'm looking down what bond axis specifically? I'm looking down, let's say, the carbon 2 to carbon 3 bond axis. So this is carbon 1, this is carbon 2, this is carbon 3, okay? All right, so if I'm looking down that bond axis and I'm going to draw the Newman projection for that, what is implied at that carbon 2 position? I have what group that's going down, that's in the same plane as the carbon-carbon bond axis, but what group is coming out of the board right now, and what group is going into the board at carbon 2? 2 hydrogens, right? So we know that there's an implied hydrogen, and we can draw one of them coming out at us, right? And there's another implied hydrogen with one of them going into the board, okay? Now, what about carbon 3? What's all at carbon 3? So carbon 3, we just see the carbon, we don't see all the other groups, right? But all the other groups are hydrogen, right? There are 3 of them. One of them we're going to draw in the plane, right, of the board. The other we're going to draw coming out at us again. And then the other is going in, okay? So again, we're trying to orient ourselves to draw the Newman projection for this guy, okay? Okay, so now we're going to take that and we're going to convert that to the Newman projection. Who do I draw first? First thing I always like to draw is the front carbon, right? So I'm looking at carbon 2. When I'm doing that, what is pointing down? That's in the plane of the board at this point. A methyl group, right? So we have a guy pointing down. It is specifically this guy. That's a methyl group. This is different compared to what we did for ethane, okay? Now, if that's a methyl group, then I have a group that's pointing up and to the right, which is a hydrogen, right, because it's coming out at us, and I have a group that's pointing up and to the left, which is another hydrogen, okay? Okay, so that's my front carbon. Now, back carbon. I'm going to change my color here. Back carbon we draw with a circle, right? That's how we represent it. Now, what is pointing directly up on that back carbon? So it's going to be in the same plane as our carbon-carbon bond axis. It's the hydrogen. It's this guy right here. We also have a hydrogen pointing down and to the right, and another hydrogen pointing down and to the right, okay? So we're taking our bond line structure, or what you could kind of consider a sawhorse structure for ethane or propane, and we're converting it into our Newman projection here. And I'm going to actually erase the blues because I forget how hard they are to see. Okay. Okay, so now we're going to do the same thing. We're going to look at the energies of these guys, okay? Exact same thing that we saw for ethane. We're going to get the lowest energy conformation in the staggered conformation. What do I have it in right now? Is this staggered or eclipsed? Staggered. This is staggered, right? So we're going to start where we have our methyl group at 180-degree dihedral angle from this bottom structure, okay? And what we're going to do here is we're going to begin to rotate. And notice that we're going to rotate this front carbon. We're going to hold that back carbon steady, okay? So as we begin to rotate this, we should see that we start at our nice little lowest energy state in our staggered conformation. As we start to rotate this to the right, what happens to the energy here? It increases because we're moving into what conformation here? Our eclipse conformation, right? So exact same thing. We continue to rotate. We get back into the staggered. We get back into the eclipsed, and we continue to do that until we get back to where we started, okay? So now note, all of these staggered conformations, are they all at the same energy level? Yes, right? So for propane, all of these staggered conformations are all at the same exact energy level, okay? What did we call that? They had the same energy. We call that specifically, these are all degenerate. So all of these staggered conformations are degenerate. They're at the exact same energy level. What about our eclipsing conformations? Are they all the same? Yes, so they're also degenerate, okay? Now, what is the only thing that's changed compared to ethane? So specifically, what is the energy difference here between our lowest energy conformation, our staggered conformation, and our eclipse conformation?
We have 14.
14 kilojoules per mole, right? So the difference here between our staggered and our eclipsed is 14 kilojoules per mole. What was the energy difference between staggered and eclipsed for ethane? Does anyone remember? It was 12, right? So what is the big difference here? Well, there's a little bit more energy required to move into this eclipsing position, right? So because we had 12 kilojoules for the ethane molecule, right, we could propose that each hydrogen-hydrogen eclipse cost how much energy?
It's 12.3. Or 4.
Right, so we had, in ethane, we had 3 different hydrogen-hydrogen eclipses. If that together cost 12 kilojoules worth of energy, then we could say, well, each hydrogen-hydrogen costs about 4 kilojoules, right? So if we do that, in this guy, we have one of these at 4 kilojoules, because we have 2 different hydrogen-hydrogen eclipses. So these two are going to cost a 4 and a 4. What is that combined? 8, right? If we know that this total energy is 14 kilojoules, then we can figure out what this methyl hydrogen eclipse cost as well, right? So if the 8 is coming from the 2 hydrogens, then we are left with about 6 kilojoules per mole of energy, and that's what we see in this methyl hydrogen eclipse. Is that right? I don't, eclipse? Yes, okay. I think I'm spelling things right today. Let me know if I'm not. Okay, so same exact thing. Propane, all of our energy levels are degenerate here. We have lowest energy in the staggered conformation. We have highest energy in the eclipse conformation. But now, given the energy difference between the two, we can hypothesize that a methyl hydrogen eclipse costs about 6 kilojoules per mole worth of energy, whereas a hydrogen-hydrogen eclipse costs a little bit less at 4, okay? Okay, so, yes?
Right, so is it always going to equal 14 kilojoules of moles, or is it just for this instance?
For this guy, the difference between these is 14 kilojoules per mole, because for ethane, when it was all hydrogens, it was only 12.
Okay.
So this allows us to predict, well, if these guys are both 4, then this guy's about 6, a little bit more. Yes?
This is probably a stupid question, but the position of the methyl group, does it matter as where you start it from?
No, so it depends on, for something like this,
Uh-huh.
it's easier just to start, okay, we're going to be here, and we're just going to rotate until we get back here,
As long as it's in the front carbon.
as long as it's in the front carbon. So
Okay.
anytime you're rotating these, and we'll get into this later, hold one steady, don't move one, and rotate the other to move through these various different conformations.
Okay.
Okay, so that's for propane, right? We did ethane first. Now we talked about propane. What about, who do you think we're going to talk about next? Butane, right? So now we're going to add in one more methyl group, and we're going to talk about the different conformations of butane. We good? Yes. Okay, so now butane's going to be a little bit different. So same thing, I'm going to go ahead and start with drawing the bond line structure of butane. Again, we're going to be focused on this carbon 2 to carbon 3 bond axis. So we're going to be looking down this guy. Again, we have similar things. We've got a hydrogen coming out, we've got a hydrogen going in, and then we've got a hydrogen coming out and a hydrogen going in. Okay? So I'm going to take this guy, our little sawhorse projection, bond line structure, and I'm going to convert that into my Newman projection. I'm going to start with this front carbon. I've got a group that's coming out that specifically is a methyl group that's pointing directly up. So this is a methyl. And then out to the left and to the right, I've got a hydrogen and a hydrogen. As I look through that bond towards the back carbon, I'll draw that back carbon. Now I've got the methyl group pointing down on that back carbon. So I draw that. And then the other two pointing up and out to the right and to the left are the 2 hydrogens, okay? So we're taking butane, we're converting it into our Newman projection, okay? So now we're going to go through the exact same thing, looking at the energy differences between both our staggered conformation and our eclipse conformation, okay? We're going to start here where we have the two methyl groups 180 degrees apart from one another. And we're going to start to rotate that front carbon, okay? So as we rotate it, we move from our staggered into our eclipse, which is normal. We're used to that, okay? But now notice as we come down, is this energy from where we started, where we had these two guys 180 degrees, and this energy, is it slightly different?
Yes.
Yes. So now we have differences in energies between our staggered conformations. We're going to talk about what that means and why we see that, okay? Also, as we move back up now into our eclipse, is this energy, where we have our two methyls eclipsing one another, is this at a different energy comparatively to when they weren't eclipsing, when they were eclipsing a hydrogen instead? Yes, okay. So as we move back down, we find that, again, we're at a similar energy here. And as we move back up, we'll find that we're at a similar energy from where we started at here, okay? So now, we have two different energy conformations in our staggered. We have two different energy conformations in our eclipse. I'm going to talk about why we actually see this, okay? Okay, so two different conformations. We're going to start with the staggered, okay? And maybe actually at this point it's helpful to get out to the model too. Okay, so this is butane. This is what we're going to start at. Again, we have two different energy conformations for our staggered conformation, okay? The first one, where these guys have a 180 degree separation. Again, that's the dihedral angle. This is what we call the anti-position, okay? So anti-position is methyl groups are farthest apart from one another as possible. As we take our anti-position, let's see here, and as we rotate it into the next staggered conformation, we move into what is called the gauche position. Okay, so this is French. It looks like gauche, but it is gauche. I know that this is actually how you pronounce gauche, okay? So this is our gauche position. As we continue to move it, we get it over here, which is also in the gauche. As we continue to rotate it, we would go back into the anti-conformation, okay? So now, which one was lowest in energy? When we had them 180 degrees apart from one another, or when we had them in the gauche position?
180.
180, okay? Could you predict maybe why that would be? This is not torsional things, right? We're not going to talk about molecular orbitals, but just think about these big, gigantic, bulky methyl groups, right? When they're far apart, that's good, they're happy, right? But as we bring them close together, all of these guys are just electron clouds, right? And so when they move kind of close to one another, even though they're on opposite carbons, you're going to have this electron cloud a little bit too close to this electron cloud, right? So what is that going to do? Do electrons like to be next to each other? No, right? So what we're going to see here is this electron repulsion. And what we call, in terms of these various conformations, or anytime we get electron groups too close to one another, we always call that steric strain or steric interaction, okay? So the term for this is steric strain or steric interaction. Higher energy because of that. So these two gauche positions are always higher in energy because of that repulsive effect, because of that steric strain. And the anti-conformation is always going to be our lowest energy conformation.
And that can be in either eclipse or in staggered.
So eclipse is different. We'll see steric hindrance in the eclipse, but for right now, in the staggered, there are two different conformations. There's anti and gauche. The reason why gauche is higher in energy is because of that steric interaction, that steric strain. And again, we actually have a value for that. So if we go back to the energy diagram, the energy difference between our anti and gauche for these guys being methyl groups is about 3.8 kilojoules per mole. And that was the difference in those two groups, or those two energy values on our energy diagram. Okay, so with that, those are our staggered conformations, right? So then now we're going to talk about the various differences in the eclipsing conformations. Okay, so I'm really going to briefly walk us through these eclipsing conformations to kind of talk about them. So we had a methyl group up top on our front carbon. We had a methyl group down below on our back carbon. So we're going to start here in the staggered to kind of visualize this, but I'm now going to walk us through the rotation of one of these so that we can see the other conformations in our eclipsing conformation, okay? So what I'm going to do is I'm going to hold the front carbon constant. I'm not going to move it, okay? And I'm going to rotate this back carbon, right? So front carbon is going to be held constant, and I'm going to take this back carbon and I'm going to rotate it to the left, okay? And so with that, I'm going to continue to just draw the front carbon as we have, and I'm going to move us into our first eclipsing position, okay? So I'm taking this back carbon, rotating it to the left, then our first eclipse is going to have a methyl here, a hydrogen here, and a hydrogen here. If I continue to do that, so we're rotating here, so rotate about 60 degrees. If I continue to do that, I have hydrogen, hydrogen, methyl. Rotating this guy again, now we have a methyl up here. We've got a hydrogen down here, and we've got a hydrogen down here. And then we do that one more time to get us through all of these. We've got a methyl up here. So now, bad circle, we've got a hydrogen here, we've got a methyl here, and we've got a hydrogen here, okay? So these are our three different eclipsing conformations. Now, we should be able to predict these guys' energies already with what we already know in theory, right? So if we look at our first eclipsing conformation, this guy, what type of eclipses do we see here? So first off, we've got a hydrogen-hydrogen eclipse, right? We've got a methyl hydrogen eclipse, and we've also got a methyl hydrogen eclipse up here, right? So we've got hydrogen-hydrogen, and then how many methyl hydrogens do we have? Two, right? So we've got 2 times a methyl hydrogen. Do we know approximately how much a hydrogen-hydrogen costs?
Yes.
It's about 4 kilojoules, right? So we've already figured that out from ethane. What about methyl hydrogen? Do we know how much those eclipsing conformations cost? That was what we just looked at with propane. That was about 6 kilojoules, right? But now in this guy we have 2 of them. So 2 times 6 gives us 12. So this eclipsing conformation total is going to be about 16 kilojoules per mole, okay? That's really ugly, 16 kilojoules per mole. So 16 kilojoules per mole. Okay, so that's that guy. We can predict that guy. We're also going to go to the third one over here because we're actually going to see the exact same eclipsing conformations, right? We have a methyl hydrogen, we've got a hydrogen-hydrogen, and we've got a methyl hydrogen, okay? So total here, we have hydrogen-hydrogen and 2 times methyl hydrogen gives us 4, gives us 12. So total we have again 16 kilojoules per mole. So these two energies are what compared to one another? They're degenerate. Okay, so they're equal. There's no difference between them. Now, the question is this guy in the middle, okay? So when we look at our energy diagram, what we find is in this eclipsing conformation, the total energy for that guy compared to the staggered was 19 kilojoules per mole, okay? In this guy, we have a hydrogen-hydrogen, we have a hydrogen-hydrogen, and now we have a methyl-methyl eclipse, okay? So with that, we have 2 hydrogen-hydrogen. Again, each of those costs about 4. So the 2 of those combined are going to give us 8. With that, and the total energy of this entire eclipsing conformation, can we predict how much energy that methyl-methyl costs?
Yes.
Yes, right? So if we take 19, we subtract the 8 from the 2 hydrogen-hydrogens, we get 11 kilojoules per mole for a methyl-methyl eclipse. So this is a methyl-methyl eclipse. So compared to the hydrogen-methyl and the hydrogen-hydrogen, this increases dramatically in terms of energy, okay? And the reason for that is, again, the torsional strain, right, which we've already talked about that we see for the hydrogen-hydrogen. But now, when this guy moves into an eclipse with a methyl-methyl, we've got a big electron cloud, So this increase in energy also has to do with the steric hindrance, with the steric interaction, okay? So the reason why this guy costs so much more is sterics as well as torsional strain. Yes?
The 19 was just given to us?
Yeah, so if we go back to that energy diagram,
Okay.
that highest, this is the highest energy conformation, and I should probably say that. This guy is highest energy. It was at 19 kilojoules relative to the lowest conformation, the staggered conformation. Yes?
Will it always give us the total energy, or?
No.
Okay.
So now, the reason why we kind of go through this and suss all these out is so now you guys are gonna try to figure out the total energy. Because we're giving you some like benchmarks. We said, okay, hydrogen-hydrogen is about 4, hydrogen-methyl, methyl-methyl. So now I'm going to give you a molecule, and you're going to try to figure out who has the highest energy conformation. Okay, so now, next slide, I've got kind of like a little summary of all of this that we've gone over. Right, so we kind of talk about these various energy penalties. You can always use these as a nice little guide to help you out. So hydrogen-hydrogen eclipses, we've got methyl-hydrogen eclipses, methyl-methyl, and then that Gauche interaction as well, okay? Now, one thing I want to note is that the book doesn't give you any more values, right? If we want to move out to, let's say, pentane or hexane and continue to add on these groups of these bonds that we're looking at, the book doesn't tell you what these guys will cost, right? But what I will say is, overall, the more carbon groups added, the more CH3 or CH2, the larger the energy penalty. The energy penalty for both the eclipsing conformations as well as the Gauche interaction as well. So both eclipse as well as Gauche. So more, let me move this guy, more carbons. Okay, so we can kind of use that as a guide to help us figure out what these various low and high energy conformations would be. Okay, so now we're going to do an example, and I'm going to give you guys a couple problems to work on to ideally utilize what we've just learned, okay? So for this example, they give us a molecule, right? And so we can name this molecule if we want to. They then state that rotating only the carbon-3 to carbon-4 bond, they want us to identify the lowest energy conformation, and then in part B, the highest energy conformation, okay? So first step in doing this, where's carbon-3, carbon-4 bond?
One with the substituent would be third.
Right.
So left to right.
So again, we have an option here. We could start numbering here, or we could start numbering here. Why would I start on the left? Why is it better to start on the left? Or why is it correct to start on the left? Right. Because we always want to give our first substituent the lowest number possible. If we started on the right, it would be a 4 compared to if we started on the left where it's 3. Okay, so that's number one. And sometimes they won't even give you the molecule, they'll just give you the name. So we're always maybe starting a little bit differently, but it's going towards the same end goal. Okay, so then carbon-3 is this guy. Carbon-4 is this guy. So we're looking down this bond, and specifically they tell us the 3 to 4, right? So my arrow is looking through 3, that's going to be my front carbon, going to 4, which is going to be my back carbon. Okay, so first step in this is taking this guy and probably drawing what?
My Newman.
Newman projection, right? So we're going to take our little bond line, we're going to take our sawhorse, and we're going to convert that into the Newman projection so we can see these various conformations, okay? Okay, so with that, I'm going to start on my front carbon, which is carbon-3. So in the same plane, what group is this coming up?
Nothing.
So we've got specifically a one 2-carbon group that's pointing up from that carbon 3. So what would we call this? We could abbreviate it CH2CH3, or we could also just say ethyl, ET. Okay, and I like to abbreviate it ET just because I'm lazy. Okay, so we're going to start there. This ethyl group is in the same plane as that carbon 3, carbon 4 bond, so it's going to be pointing directly up. So now, again, we're looking this way. What's pointing down and to the right for this carbon 3? What is this group specifically? A methyl, right? So this is just a methyl. It's pointing down and to the right. And again, it's smart to kind of orient yourself to see that, yes, coming out is pointing to the right. And then there's an implied little guy here, which is pointing down to the left, which is hydrogen. Okay, so now we're looking through that bond. We can't see that back carbon, but we represent it as a big circle. What is pointing down on that back carbon? So again, we have a 1,2 carbon chain here. So we can also identify this as an ethyl group. It's pointing down. And then on that carbon 4, we have 2 other things coming off, pointing to the right and to the left. What are both of those? Hydrogens, okay? So first step in this is getting the correct Newman structure, Newman projection from the bond line structure, okay? Okay, so in A, they want us to take this, and they want us to tell them what is the lowest energy conformation. So who am I going to be concerned with here? My eclipsing conformations or my staggered conformations if I want lowest energy?
Yes,
Staggered. Okay, so the first part we're going to look at just the 3 staggered conformations and figure out who is going to be lowest in energy. Okay, so we already have one, right? So we're already in our staggered conformation from our bond line structure. What we're going to look at right now are the penalties of being in the gauche position, right? Because for staggered, that's the only thing we have to care about is those gauche positions. All anti-positions are not going to have any penalty. So for this first conformation, who's gauche? And again, a hydrogen with another thing, with another carbon chain, that's not a gauche interaction. The only thing we're looking at is carbon chain in a gauche position with a carbon chain.
So the ethyl methyl group?
Right, so here we have the ethyl methyl. So we have an ethyl methyl gauche. What about ethyl ethyl? Where are they relative to one another?
Opposite.
Right, so they're anti at this point. So this guy is gauche. And then we have ethyl ethyl in the anti position, which is good. So this is going to be conformation number 1. ET ethyl. Oh, sorry. ET ethyl. Okay, unfortunately there's 2 other staggered conformations, right? So what should I do to this guy to get to the next one?
Keep front.
I'm going to rotate somebody, right? So now for this one, what I would always suggest is keep the one that has the less substituents constant. So who has less substituents, the front carbon or the back carbon?
The
Back carbon. So we're going to keep back carbon constant. We're going to rotate front carbon. So that was actually probably stupid of me. So back carbon's constant. We've got ethyl. We've got hydrogen. We've got hydrogen. We're going to rotate that front carbon to the right. So now front carbon is going to have an ethyl here, is going to have a methyl here, and is going to have a hydrogen here. And we're going to go ahead and do the next one because we have to get to it anyways. So same thing. I'm going to rotate front carbon, again, to the right, keeping back carbon constant. So hydrogen, hydrogen, ethyl. Now we'll have ethyl here, we'll have methyl here, we'll have hydrogen here. So these are our 3 conformations. This guy goes for conformation number 1. Okay, so then conformation number 2, which is this guy. What type of Gauche interactions do we have here?
We have the ethyl methyl and ethyl ethyl.
Right, so now we have this guy in a gauche position. Then we also have this guy in a gauche interaction. Okay, so we have at this point an ethyl gauche, and we have an ethyl methyl gauche as well. So both of these are gauche, which is bad. Okay, so then finally we get to the last guy. This is our conformation number 3. Now we have a ethyl-ethyl gauche. So we have ethyl-ethyl, and we have a methyl-ethyl. This is anti, which is good. So if we're looking for lowest energy, who are we really comparing, right? One of these is too much.
Right.
It's too many Gauche interactions. It's not going to happen, right? So if we're looking at lowest energy, we're probably going to ignore number 2 because we have 2 Gauche interactions. It's not Gauche, it's Gauche. Damn it, okay. The entire presentation. Gauche interactions, okay?
It is Gauche.
It is Gauche. Now, pardon me. This is s'il vous plaît, I don't know. Okay, anyways. Okay, so number 2, we're ignoring. It has ethyl-ethyl gauche. It has ethyl-methyl gauche. Number 1 has an ethyl-methyl gauche, ethyl-ethyl anti, and number 3 has ethyl-ethyl gauche, methyl-ethyl anti. Again, the more stuff gets added on, the larger the energy penalty. So who do you think is going to have a lower energy? Number 1 with that ethyl-ethyl in the anti position, or number 3 with that ethyl-ethyl in the gauche position?
The lowest energy?
The
Lowest energy.
Number 1.
Yeah, number 1.
So again, we want the big groups to be as far away from one another as possible. In number 1, ethyl and ethyl are in the anti position.
Correct.
Right. Okay. Yes. You're right. Yes. So number 1, because of that, is our lowest energy conformation. Okay. So number 1 is lowest energy. So we start moving things. Okay, so now for part B, that was lowest energy conformation. Part B, they want us to find the highest energy conformation. So, what type of conformation am I going to be looking at if I'm looking for highest energy?
An eclipse.
The eclipsing confirmation. So again, there's 3 of them, unfortunately. To find them, we're going to take the same thing. We're going to rotate one of the carbons. I'm going to go ahead and rotate the first carbon because I like to just be different and just contradict myself and pronounce Gauche wrong the entire time. So I'm going to rotate this front carbon. Nope, I'm going to hold the front carbon steady.
Okay.
I'm going to rotate the back carbon, pardon me. So back is going to rotate to the left, clockwise. Okay, so first thing we're going to find, we're going to have a hydrogen here. We're going to have a hydrogen here, and we're going to move that ethyl here. So we have one of these guys. Same thing. We've got ethyl, we've got methyl, we've got hydrogen. We're going to rotate again to the left where we get the ethyl, we get the hydrogen, and we get the hydrogen. And then one more time to get ethyl, methyl, hydrogen, to get hydrogen, ethyl, and hydrogen. Okay, so all I'm doing, I'm holding that front carbon steady, and I'm just taking that back carbon and I'm rotating it 360 degrees. Okay, finding the various eclipsing conformations. So now, we can calculate-ish kind of the energy penalty for all of these 3. One of these is going to be the highest energy conformation, okay? So in this first one, what type of eclipsing interactions do we get? We get an ethyl hydrogen, right? We get another ethyl hydrogen, and we get a methyl hydrogen, okay? So we can assume those are all kind of like the methyl hydrogens, right, which ended up being about 6. So we could say, okay, this is about 18 kilojoules-ish per mole. That's approximate. As we move into the next one, we get a hydrogen-hydrogen, we get a methyl-hydrogen, and now we get an ethyl-ethyl eclipse, okay? So again, if we think back to butane, What was the most energy penalty? What eclipsing interaction was the highest energy penalty? It was methyl-methyl, but then I also said the more carbons you put on, the larger the penalty overall. So in this guy, we've got an ethyl-ethyl eclipse, which is really, really, really bad energetically, okay? So this guy is going to be very high. If we go ahead and look at the last one, we've got a hydrogen-hydrogen, we've got an ethyl-hydrogen, and we've got a methyl-ethyl. Methyl-ethyl will be bad, but do you think it will be as bad as an ethyl-ethyl eclipse? No, okay? So from that, again, we have conformation number 1, conformation number 2, conformation number 3. The highest energy conformation is when you have these ethyl groups eclipsing one another. Okay, so conformation number 2 is our highest energy conformation. Who would you kind of predict to be the second highest energy? The ethyl-methyl eclipse. So number 3 here would be the second highest energy, and then number 1 would be the third highest energy conformation, because it's all those hydrogen with carbon groups. So this would be second highest. Okay, so another little question that you could get from stuff like this is not only determining the highest energy or the lowest energy, which is what we've just done, but also saying how many different energy conformations are there, right? So for this guy, we're talking about the highest energy conformations. How many different energies did we get as we move through looking at all these conformations?
Altogether?
Altogether, just these 3 at the bottom. How many different actual energy conformations, if you drew one of those energy diagrams, how many different values would you get for these eclipsing conformations?
3.
You get 3. They're all different, right? When we looked at the butane, 2 of them were the same. Right? 2 of them had the exact same eclipsing conformations. Here, though, you can see, these are all going to be different. And so you would say, there's 3 different energy conformations as this molecule moves through its eclipsing conformations.
And that's because we have
3 different actual eclipsing situations. Like if this had been the exact same as this, if we had calculated they're all ethyl hydrogen, then there would only be 2. But because each of these is different, there would be 3 different energy conformations.
Wait,
But
so if for this molecule, there's 3 different energy conformations?
No, so for this molecule, there are 3 different highest energy conformations. Right? If we had, again, drawn that energy diagram, those humps up here, you would have 3 different actual humps, 3 different values. None of them would go back to the same spot because they're all different compared to one another. Okay, so with the remaining time, I want to go ahead and try some of these, okay? So I have molecules on the next slide, and I want you guys to identify the highest and lowest energy conformations for both of them. This one looking down the C2 to C3 bond, and this one looking down the C3 to C4 bond. Okay, so we went over the first one in class. We'll do the second one on Monday, but I'm going to go ahead and run through the answers to both of them so I can post this. For the first one, again, we're looking for the highest and lowest energy conformations for the following molecules, right? So the first one, they want us to look down the carbon 2 to carbon 3 bond axis. And so when we're numbering this, we would start with 1 here, because again, our first substituent, this guy and this guy, are going to come at the 2 position, as opposed to them coming at the 1, 2, 3 position. So we have carbon 1, carbon 2, we've got carbon 3 and carbon 4. And so they want us to look down this bond axis, okay? So if we draw our weird, creepy eyeball, which we shouldn't, we'd be looking down this bond axis. Okay, so first thing I'm going to do is I'm going to draw the Newman projection for this as is, okay? So if we're looking at this front carbon, we've got a methyl group that's going down, right? So we can draw that, and again, I'm going to abbreviate that as Me, as methyl. And then we've got a methyl group pointing up and to the right, and a methyl group pointing up and to the left. So we've got Me here, and we've also got Me here, okay? So now we're looking down this bond, right, and looking at the back carbon, which we represent as our circle. We've got a methyl group that's pointing up into the plane, and then we've got a hydrogen. Let me get rid of this guy. We've got a hydrogen that's coming out, and then we've also got a hydrogen that's going in. All right, so that's going to be out into the, or down into the right, and then down into the left. Okay, all right, so that's number one. All right, so we're going to look for lowest energy first because we're already in the staggered position, and we know that our lowest energy conformation is going to be one of our staggered. The spelling to me, and just today, staggered is hard. Spelling is hard. Staggered. No, I bet it is AR. Anyways, okay, it doesn't matter. So we're in our staggered position. We know we're looking for one of the 3 staggered positions to be our lowest energy conformation, okay? So what I'm going to do is I'm going to actually keep that front carbon steady. So I'm going to keep front carbon steady. It's not going to move. And I'm going to rotate our back carbon. So we've got methyl, methyl, methyl. If I rotate this back carbon to the right, we're going to have our hydrogen up. We're going to have our methyl down and to the right, and then a hydrogen here. And then we're going to do the exact same thing again. And let's be a little bit more neat. We've got down to the left and to the right. We've got a methyl, we've got a methyl, we've got a methyl. That back carbon now is going to have the methyl group out here. We're going to have our hydrogen out here and our hydrogen out here, okay? So now if we look at all of these staggered conformations, what we're going to find is that each one is going to have a methyl-methyl gauche and a methyl-methyl gauche, right? These interactions we don't care about because they're not going to have any energy penalty. Here we have a methyl-methyl gauche and a methyl-methyl gauche. So we have 2 methyl-methyl gauche. We have 2 methyl-methyl gauche. Again, these guys don't count. And then here we have 2 methyl-methyl gauche as well, okay? So for all of these staggered conformations, because that front carbon is essentially has the same substituents off of it, all of these guys will have the same energy, right? So all of these guys will have the same energy. Again, they're all degenerate, and any one of these would count as the lowest energy conformation. So if you had drawn either 1 or 2 or 3, they would all be considered our lowest energy because they all have the same energy. Okay? Okay, so then from there, we can move to the highest energy. For the highest energy, again, we're looking at all of the eclipsing conformations. So if I go ahead and start where I was, so I'm going to have that front carbon steady. I'm going to take this guy, and again, I'm going to rotate it to the right, but now I'm going to depict my eclipsing conformations. So we hit that methyl-methyl, we have a hydrogen, we have a hydrogen. Same thing, I'm going to continue to rotate that back carbon. So we have methyl, methyl, methyl. Now we're going to have the methyl group here. We're going to have the hydrogen here and the hydrogen here. And one more time, we'll get our final conformation, our final eclipsing conformation. And again, now we've got the methyl group here, we've got the hydrogen here, and we've got the hydrogen here. Okay, so these are going to be what we're looking at for our highest energy conformation. And again, what we're trying to do is compare the 2, or compare the 3. Okay, so here we know that methyl-methyl eclipse costs like the most energy comparatively. So here we have 1 methyl-methyl eclipse. We have also a methyl hydrogen. So 1, and then we have another methyl hydrogen. So overall, that is 2 methyl hydrogens. Right, and we could kind of predict with respect to knowing some of these energies. A methyl hydrogen is about 6 kilojoules. Methyl-methyl, and there's 2 of them, a methyl-methyl is about 11. So this is 12 plus 11. 12 plus 11 gives us 23 per mole if we wanted to predict the actual energy state. As we move to the next guy, so this will be conformation number 1. As we move to the next guy, we'll find methyl hydrogen, and methyl-methyl, right? So now, same thing. We get a methyl-methyl eclipse. we get 2 methyl hydrogen eclipses. So again, this is also 23 kilojoules. It's the same exact energy. And then for number 3, again, we get a methyl-methyl, and then 2 methyl hydrogens, right? So we get 1 methyl-methyl, and then 2 methyl hydrogens. And so again, we get 23 kilojoules per mole of energy. So just like we saw for the staggered conformations, all of our eclipsing conformations have the same energy. They're all degenerate. So if I had asked you to draw the highest energy state, you could have drawn any of these 3, and that would have been an acceptable answer for the highest energy conformation. Formation. Okay, so that is question 1, right? So the other one over here, same exact thing, except now they want us to look down the carbon 3 to carbon 4 bond axis. So again, if we were numbering these, we would start 1, 2, 3, 4. So they're wanting us to look down this guy with our eyeball here. So I'm going to take this and I'm going to move it over here. So I have some room. And as pointed out in class, I think we've done this one, but I'm going to go ahead and go through it. You can just stop listening to me at this point. So I'm going to look at that front carbon first and note that we've got an ethyl group. So I'm going to abbreviate that ET because I like to do that. So that's going to be my front carbon pointing down. So this is ethyl. I've got this thing, this methyl, that is, at least as we orient ourselves looking at this, it's coming out of the board. So to me, looking down this bond, that's going to be up and to my right. So this is a methyl. And then up and to my left is a hydrogen. So I want to make this a little bit prettier. Hydrogen. So this is a methyl, and this is a hydrogen. And so now that's my front carbon. I'm going to look down through this bond to my back carbon. Pointing up is another ethyl group. So we have ethyl here, and then we have pointing down hydrogen, hydrogen. So pointing down to the right and left is a hydrogen, hydrogen. Okay, so highest energy or lowest energy we'll start with because we're already in the staggered conformation. So now we're going to look at the different staggered conformations starting from where we're at. We'll say this is our number 1 conformation. So again, I'm going to go ahead and keep my front carbon steady. And I'm going to move my back carbon, and I'm going to draw this better. Front carbon steady, going to move my back carbon. So we've got methyl, ethyl, hydrogen. I'm going to go ahead and draw my kind of my skeleton for all of these. So methyl, ethyl, hydrogen with back carbon. So now if we're rotating this back carbon to the right, in my second conformation, I'm going to end up with ethyl here. I'm going to end up with hydrogen here and hydrogen here. And then again, if we do the same exact thing, we keep rotating, I'm going to end up with ethyl here. I'm going to end up with hydrogen here and hydrogen here. This is number 1, number 2, and number 3. Okay, so again, we're going to look at all the different interactions that we're getting in these staggered conformations. Most specifically, we're looking for gauche interactions. Gauche. So first one that we see here is we have an ethyl-methyl gauche. And then everything else is just hydrogen ethyl, so we don't have to worry about that. So this is gauche. Here we've got a methyl-ethyl gauche and an ethyl-ethyl, so that's bad. Ethyl, we've got methyl, ethyl. So there are 2 gauche interactions here. And then here we've got an ethyl-ethyl gauche. Ethyl gauche. Okay? So again, if we're looking for the lowest energy, we want the least energy penalty gauche interaction, right? And again, as these guys get bigger, as the carbon substituents coming off of these guys get bigger, that energy penalty for being in the gauche position gets worse, right? So because of that, this is going to be the highest of the lowest energy, right? So highest of the lowest energy, est energy. This would be second highest, so second highest because it's ethyl, ethyl. And then this guy would be the lowest energy conformation because it only has one gauche interaction. It's an ethyl-methyl gauche. Okay? So another question again could be, rank the various conformations. And so here, in terms of like energy, going, let's say, from the lowest energy to the highest. And if we wanted that in this type of situation, we'd say, lowest energy is number 1. And then that's going to be less than the second lowest or second highest, whichever one you want to say, which would be number 3, which would be less than number 2. Okay? Okay, so again, lowest energy is number 1. It's with that methyl ethyl in the gauche position. So then if we're looking at highest energy interactions, so again, we're going to be moving into our eclipsing conformations. And I'm going to go ahead and draw my framework here. So I've got ethyl methyl, hydrogen, rotate. We've got ethyl, methyl, hydrogen, rotate. And we've got, again, ethyl, methyl, hydrogen. So now we're just going to rotate that back carbon. So the first one that we get into is this guy, ethyl here, hydrogen here, hydrogen here. The next one, if we keep rotating, is going to have a hydrogen here, an ethyl here, and a hydrogen here. And then again, if we keep rotating, we're going to have our ethyl here, our hydrogen here, our hydrogen here. Okay, so these are our 3 eclipsing conformations where we're looking for our highest energy conformation, right? So if we start over on number 1, all of these guys, we have a methyl-ethyl eclipse, we have a hydrogen-hydrogen, and a hydrogen-ethyl. So if we keep track of just carbon eclipses, right now in this one we've got a methyl-ethyl. Since we know those are going to be really taxing energetically or taxing or have the highest energy penalty. So the other ones are just hydrogen, hydrogen, ethyl. So hydrogen, hydrogen, and then hydrogen, ethyl. Same thing here for number 2. We've got an ethyl-ethyl eclipse, which is bad. We've also got a hydrogen, hydrogen, and then a methyl, hydrogen. And then for number 3, let's draw 3 a little bit better. We've got all hydrogen alkyl group eclipses. So we've got a hydrogen ethyl. We've got 2 hydrogen ethyls, so 1, 2, and then we've also got a hydrogen methyl. So pardon me, I kind of back those or reverse the way I normally write these guys. I'll go ahead and change that. Okay, so I've got 2 ethyl hydrogens, and I've got 1 methyl hydrogen. Okay? Okay, so again, hydrogen, hydrogen, or hydrogen methyl, hydrogen ethyl, they're taxing, right, in the eclipsing conformation, but the really, really, really energetic one is going to be the ethyl, methyl, or ethyl-ethyl eclipse. So the ones that we're really considering right now are the ones where we actually have these carbon groups in these eclipsing conformations. And again, the larger that carbon chain, the larger the energy penalty. So because of that, number 2 with its ethyl-ethyl eclipse is going to be our highest energy conformation. Okay. And so again, I would take this, I would go do some homework, I would try to start drawing these and visualizing because they're not the easiest thing to do, but I think once you get the hang of it, it's not super hard to see which ones are our highest and lowest energy conformations.